Welcome back to the millimeter wave for 5G and beyond. So, today we will be covering the lecture number. Things that we will be covering are the following. So, you are starting the WebDM part. So, because of that WebDM there is a motivation, and in the last class we have given a simple motivation of how to remove the inversion part at the receiver side, okay, and we have been successful in doing that. But let us go back to that equation again, whatever we have drawn in the last class, and let us see is there any problem with this approach. Now, apparently it does not have any problem, apparently. Why? Because you see in the receiver there is no equalizer, there is no inversion. So, this is just a U star, I can think of it as an equalizer, and this precoder is a V, that is also some sort of a matrix multiplication. Then what is the issue of this scheme which motivate us to go to some other concept or some other platform? The whole problem, see, I solved one problem. What is that issue? The issue was inversion at the receiver. I solved that, but I invite another issue. What is that issue? Issue is that how do I do a singular value decomposition of this matrix channel matrix, because that is also not a very easy task. If the dimension of this channel matrix is becoming larger, getting a singular value decomposition is also probably, I would say, equally tough or equally comparable in terms of the computational complexity with respect to the inversion. Inversion is even tough to get it. Singular value, probably there are efficient algorithm, you may get it slightly easier, you may get it with slightly easier complexity, but still it is not reduced to a very simple one. You still have this complexity. So, that means the bottleneck, you solve one problem, but you come up with a slightly lesser issue, but still that is a significant problem called a singular value decomposition. Okay. And second problem, this is the first problem, that singular value decomposition has to be done, because then only, because ultimately you have to know U matrix, you have to know the V matrix, right. So, if you do not know U and V matrix, there is no point. So, know that part. That is the second issue. Second issue is that if you notice, if you look at the transmitter side, the transmitter, this equalizer, this precoder WBBT equal to V, I am conveniently writing it, but where will the transmitter know that? How will it get V matrix? Somebody has to tell it, right. Either this particular channel matrix has to be broadcast to transmitter side and the receiver side both, and then singular value decomposition, or this V matrix can be can be developed at the RX side itself. You can do SVD and then you feed it back to the transmitter. So, what it essentially means? It means that this particular precoder design mandates that you need to know the channel at the transmitter side, and that itself is a tricky task to have it, because by the time you get your channel, because what is easier to know? The easier to know is that the channel should be at the receiver side, and it is very convenient to have it, okay, because you have a pilot, you can estimate your channel at the receiver. Now, to know the channel back to the transmitter, either you have to transmit this whole channel back to the transmitter using the protocol, or you have to or you have to re-estimate your channel at the transmitter side, assuming receiver is your transmitter, and if you assume some sort of a duality, probably that may or may not hold all the time, because if you have slightly movement, that may not work. So, the feeding back this information to the transmitter itself is an overhead, that is what I am trying to say. That means, this particular V matrix, you have to feed it back, you have to somehow feed it back from receiver to transmitter, and that is a overhead, it is a huge overhead. Okay. But I want that, because I have to I have to reduce my complexity at the receiver, but I am increasing complexity at my transmitter. So, now the question comes, can I have a scheme where I am achieving both, meaning I am having this kind of receiver, whatever is shown here, where where I have to, your receiver is nothing but some I mean, at the end of the day your receiver will give you this kind of data model, where it is just like a diagonal matrix data plus noise, because then only I can avoid the inversion. And at the same time, without I am making the point clear, without any channel component feedback, I will design my equalizer precoder. That means that V matrix, the precoder matrix, I know it upfront at the transmitter side without knowing my channel. Nobody gives me any feedback, and question is how is it possible, right? So, the problem statement is the following. The problem statement is, we want V at T x without knowing channel. That means, I am developing a V which will exactly do what the other system has done, but I really do not know what my channel is. So, that means, my V should be a channel independent component. Okay. How is it possible? Because if we say V is a SVD component of my H, then how can I develop a V without knowing a channel? It is a chicken and egg problem, right? Because you have to first know H, then only you know V. Now, I am saying no, I do not want to know H, but I can develop a V. So, how can I guess even a V when my channel itself is not known to the transmitter side? Okay? And that is a very interesting problem statement. So, can I have that kind of system? Can I create a channel, or can I have a channel where I know it is V without even knowing the channel? You understand the problem? Okay. And my dear friend, that is a, it is possible, really it is possible. Okay. How is it possible? If my channel, whatever channel I am saying that, instead of a Toeplitz matrix or any other matrix, it can be Toeplitz matrix if it is a CISO FDM case, it can, if it is just a MIMO case, then it can be just normal, like a normal H, meaning it is a matrix. Both are matrix, but it will not have any structure, because we are talking in the context of CISO. So, let us assume H only. So, H instead of Toeplitz matrix, if this matrix is a circular matrix, let us see what is meant by a circular matrix. Circular matrix is basically, if I have a matrix, say let us say I have A, B, C, there are 3 elements. So, circular matrix meaning the row will be circularly shifted. In the Toeplitz, what is happening? What is happening in the Toeplitz matrix? In the Toeplitz matrix, the rows are not circularly shifted, it is only right shifted or left shifted. We have seen a right shifted Toeplitz, you can also have a left shifted Toeplitz, but it is not a circular. When you say circular, it means that it is right shifted, but whatever is shifted out, that comes back. So, which means that if ABC is the first row, the circular shift of ABC would be A would be here, B would be here, and C, which was going out, it actually comes back here. Okay. So, that is called a circular shift. Then further, if you do it, the A will be here, C will be here, and B that comes back here. I put a different color so that you can understand. So, let us say I put a different color. So, it is A, B, C, this will be A, this will be B, this will be C, this will be A, this will be C, this will be B. So, that is the matrix. This is a circular matrix. Okay. Now, what is so great about this circular matrix? Why I am talking about all this? Because there is a very interesting property of a circular matrix. The property of the circular matrix is that you can always do eigenvalue decomposition of a circular matrix in this way. If H or H is H, you can think of it any matrix, which is a circular matrix like this kind of structure. So, it will be, the property is that if H is a circular matrix, then I can break the H. Break meaning I can do some decomposition, but it is not a singular value decomposition, rather it can be an eigenvalue decomposition, but that is okay. I mean, we do not care whether it is a singular value or an eigenvalue decomposition, as long as I create some decomposition I am fine. You can have a QR decomposition also. So, in this case it is a eigenvalue decomposition. So, I can say it is a eigenvalue decomposition. Eigenvalue decomposition. If it is an eigenvalue decomposition, that is a matrix property. It says that if any matrix is a circular matrix, of course it has to be a square matrix, then only you can have the eigenvalue decomposition here. So, obviously I am talking of, this is also another point. If you look at the other problem, their channel matrix was not a square matrix, right, because it was m cross m plus l. But now I am putting a restriction. What if H is a circular matrix and a square matrix? Now, we will see in a single antenna case how do you get an H which is circular and square. Is it really possible, or I am artificially creating that kind of thing? So, that is the point of OFDM. Okay. So, if these two properties are satisfied, circular and square, then I can have an eigenvalue decomposition of H as, let us call it still a sigma H, then it is not it is not a singular value, but rather eigenvalues. I can always break it like that. Now, what is F? F is FFT matrix. That means, if H is a square and circular matrix instead of a Toeplitz matrix, I can always have eigenvalue decomposition of this H as that. These three matrix I can break it, F star, sigma H, F, where F is a FFT matrix. Now, you see FFT matrix, is it dependent on H at all? Suppose this H is a n cross n matrix, okay. Then this will also be n cross n, this will also be n cross n, and naturally this will also be n cross n, all are n cross n. So, it is a FFT matrix. And what is the structure of an FFT matrix? Structure of FFT matrix is the following: 1 1 1 1 omega, omega square, omega to the power cube and all, then 1 omega square, omega to the power 4, omega to the power 6 and so on, like that. What is omega? It is e to the power j 2 pi in this case it will not be the case. So, it will be, yeah. So, f will not be there, 2 pi f, yeah, omega. So, it is a, that is the point here. Okay. Now, the question is, what am I bringing it here? Okay. I am bringing a standard matrix structure. Now, this F is a FFT matrix, and as F is a standard matrix, it really does not depend on H. No matter what your H is, as long as it is circular and square, this F is constant and the dimension is fixed. F is independent of your H. Now, assume, go back here, go back. Is this the clear? Assume your H, assume H is square and circular, then what will happen? What will be this WBB? It will be, what should be the case? Then it will be F star, inverse FFT. What is this U? This will be F only. Now, you see In case this H is made square and circular, at the transmitter side, I really do not have to know what is my channel. I just blindly put F star, because F star would be the other side of the matrix. And here also, this for this U, I really do not have to know my channel. I have to just I do not have to do any SVD. That is what I am trying to say. Without doing any SVD, I can get my U matrix. So, this F and F star, or rather this equalizer and the precoder are freely available now, without any effort. Why it is called without any effort? Because I really do not have to know my channel for my precoder and my equalizer design. Now, do I have to know channel? Yes, that is for final decoding. You have to know the channel, because equalizer, because your eigenvalue still you have to know it, right? But that is simpler to do it. I will also show you that is also very simple to know. Okay, for a matrix, you really do not have to do any eigenvalue decompositions, big steps to find it out. It's very simple if it is a circular matrix. Now, the question would be, how do I really make this whole system a square and a circular channel? Okay, so that is where the OFDM really comes into picture. Okay. So, which means if I really do not know the channel, I can reconstruct my precoder and equalizer. Now, let us see how can I make my channel a circular matrix. Okay. So, let us take a very simple case, so that it will be easy for you to understand. Let us take a simple case. Let us say my channel is just channels transfer function I am talking. It is a, let us take an example. Let us take I am taking, let us say I am taking only 3-tap channel, simple 3-tap channel. Okay, 3-tap channel. Okay. Then what I do is the following. I had my S vector. Okay. Then what I said, I multiply my precoder with my F star matrix, because I have decided, somehow I am confident that I will make my H circular and square. So, I blindly put my equalizer, blindly put my precoder as F star. That is what I have said. Okay. Why? Because even if there is a channel, I break it like a F sigma H and F star, sorry, opposite. F star. I hope I have made the other, but yeah, F star sigma, because this is the decomposition, and then because, and here the S has to be coming with the equalizer part, with the precoder part. So, obviously, the counter part will be F star. So, that is the reason I have given, and obviously that. Okay. So, now it is clear. So, now let us say this is what I am transmitting. Instead of transmitting this vector like that, what I do, let us assume that I am taking its length as n. It is an n length equalizer, n length precoder. Okay. So, it means that I am serially sending n number of data, which will go through this particular matrix multiplication. So, this will be my n cross 1 length vector, this will also be n cross 1 length vector. So, tentatively my x cap x bar is equal to yes, this is what my data model now, and this is what I am going to transmit, but hold on, I am not transmitting x directly. What I do is the following. So, which means that this is my data x of 1, x of 2, x of n. This is my data. These are my data I am sending it, right. This is that n length data I am going to send it. Now, instead of sending this directly, That means x1 is the first data to be sent, x2 is the second data to be sent, and so on and so on. This is a vector, but finally I have to transmit through one single antenna. So how do I transmit a vector? Vector I cannot transmit in a single time. So what I do is that I am transmitting x1 first, then x2 first, and then xn first, like that. So serially I will be transmitting. So you can think of that there must be some sort of a parallel to serial converter here. Parallel to serial converter here, and that I will feed it to the antenna. But here I will have to do some more things. What I do now, what I am doing is that instead of sending this whole vector serially, I mean serially I have to send it, but instead of sending like x1, x2 and so on and so forth, I piggyback the last k length vector and put it back into the front. Okay. So, what does it mean? Let me just put this part slightly top, so that it will be easy to write it here. So, x bar is equal to f star s bar. Okay. Now, what I do here is the following: the last k length part I piggyback. Okay. So, in this case, let us assume as my channel length is 3, I take k is equal to 3. I will show that you should take k equal to 3, 4, 5, that is more than my channel length. So, k should be always greater than my channel length, greater or equal to my channel length. So, in this case, as the channel length is 3, so I am taking the last 3 and piggyback it here. So, what I am saying is this is my xn. What is my n? N can be whatever you think of. I am not getting into that direction, how spectrum of the WebDM and those kind of thing will come into picture, because that is more of a wireless communication topic, but this is more of a millimeter wave topics. So, I assume that that part I am not, that part probably may be knowing it, and you can, if not, you can always do a simulation and see what are the spectrums and all. So, that is totally a different part. Now, what I am saying is this part, this xn part, I am just piggybacking the stuff here. So, that means the last 3 I am putting it here. So, it should be xn, xn minus 1 and xn minus 2. Now, this is my new data length. Okay. So, this is L length plus I add extra 3. So, let us assume this is my n plus 3 length. Okay. That is precisely what I am doing it here. Okay. So, that is my length. So, instead of x, what I am saying is that I piggyback this, and now this is my first data, this is my second data, this is my third data, this is my fourth data, and so on and so forth. And last one, sorry, here there is a small mistake. It will be going up to here, n plus 3, total data. Total data is like that. Okay. Now, this is the data I am sending. First xn minus 2, xn minus 1, xn, then x1, x2, x3, blah blah blah. All things are coming. So, that how many data I am sending? N plus 3 instead of n. And what is the n? N can be, you take up your numbers. Now, if it is an FFT, it should be some 2 to the power m format, like 16, 64, 128, 256. And how you determine that? That's again, it's a separate topic. I am not getting into that. Okay, so, let us assume n is fixed for you. Okay. Then what will happen? What are the interesting stuff that will come into picture here? The interesting stuff that will come into picture here is that, so your first data is xn minus 2, xn minus 1, and so on and so forth, right. So, now what I do at the receiver I am just, I can just take the first data, let us draw few, so that you can easily understand what I am saying is. Then there is a, this is what it is, right. Now, what is y1? Y1 is, what was the channel? Channel was H0, H1, H2, right. So, if I send xn minus 2, that is my first data, right. So, that is my first data. Then next come x n minus 1 and so on and so forth. Okay. So, what is my data? It will be h 0 x n minus 2 plus h 1 will be here. It is a garbage. Why? Because it is some data which was happening previously, right. So, I call it some garbage. So, let us call it I do not know what is the best notation, but let us call it some cross. I just noticed it is a previous data, that means before x n minus 1 sorry, before x n minus 2 what was the previous data, plus h 2, again that is some garbage. Clear? Then I go to next one. What will happen? Here what will happen is that here plus h 2 this will be a garbage. What about a y 3? This will be x 1. Yeah, I should write it capital M. Okay. This will be 1. This is what it is. You can have similarly y 4 also. What will be the y 4? Here interesting point, this will be x 1, because that is the first, right. Y 4 meaning at fourth position I am here. So, that is the first data and subsequently the other 3, right. So, this would be h 1 and so on and so forth. I spent some time to complete this part, and you can have n y n plus 3. So, the last one. Let us complete that part. Okay. So, this will be h 0, this will be x 1 plus h 1 x n minus 1, okay, plus h 2 x n minus 2. Okay. That is what it is. Correct? Okay, very good. This is what my last data. Now, what is my next job? Stack it together and find out. Okay, fine, let us do that. Okay, so let us do that. So, let us say I stack the whole thing. Stack means this whole data. I stack the whole thing. Okay. So, what will I get? I get h 2, h 1, h 0, then it will be all 0. Then this will be, we have seen it, right, h 1, h 0, blah blah blah. Finally, at some point of time h 0, h 1, h 2, 0 0, like this. This is what I will do. Toeplitz matrix. There is nothing so great about it. So, what will happen? First two terms will be for S vector, first two term will be garbage, garbage meaning from the previous frame, something like that. Then what will I get? You can just construct it from here. What's x n minus 1, x n minus 2, and so on and so forth. So, it will be x n and blah blah blah, all will be coming into picture here. So, there is nothing great about it. Okay. Then I just do one small change here. What is the small change? Small change is that I discard the first 3 elements. That means, when I stack it all of them together, I may find uh, everything is like a two-page matrix. So, instead of taking this whole thing together like that, I start taking from here onward. Okay? That means the first 3 I discard it. Got it? The first 3 what I do? I just discard it. Okay? Now, you think from y4 to yn plus 3. So, now instead of this you just take, if I just take them together it will be two-page matrix. Now, I am saying that hey, I am actually not taking all of them together, rather I just discard this part and I discard this part. That means I receive it, but I do not consider it. I start considering only from y4, that is my point. Okay. Now, you think this is H0, H1, H2, but who is there? Xn, x1 minus 1, x1, right. So, let us go back to your model. Instead of this, now I am saying that you find out y4. What will be the case? Let us say I stack it together like this: x1, x2, xn, xn minus 1. What will be the case? It is H0 x1, but H1 will be x1 and this one, right. So, what does it mean? It means that with this will be H0, right, but with xn who is there? H1, and this will be my H2, rest of them will be all 0. Okay. Similarly, when I put it y5, I am just doing some surgery. I am not doing any surgery, I am just doing rearranging. This is what it is coming, right. What is y5? You see this there. What is y5? Obviously, this will be shifted back. Okay. So, you can check it, it will be H1, H0, H2, all together y n plus 3. You will see this will be H0, H1, H2, rest will be all 0. Now, see what is the nature of this channel. Now, what is the length here? Now, I stack it together. This is what I have stacked. I have not done anything. I have just stacked them from y4 to n plus 1. So, this is n cross 1. This will be n cross n, because this itself is n cross 1, x1 to xn, right. Okay. Now, look at the nature of this channel now. Now, you can think of this is a matrix, right. This is a matrix. Now, look at the nature of this matrix. Actually, this is a circular matrix, because H0, H2, H1, look at the next row. It is like you shift it to the right side and put it back. So, this H1 comes back here. It is a circular shifting. So, now again, so which means I got back my data, I got a data model which I call it y bar, let us call it, and I got a channel, I got x bar, v bar, and all their dimension is n, this is n cross n, this is n cross 1, this is n cross 1. But now, this particular channel, let us call it HC to ensure that it is a circular channel. This channel is basically a circular channel. In our earlier case, it was H2 H1, then it will be H1 H0, H2, and finally, all will be 0, H0, H1, H2. This is how my channel is. You can generalize it, of course. Okay. So, now I am done. So, it is what is my equivalent model. So, which means this is my S bar, and I put F star as a precoder matrix, then I do some addition of my data and then I send it back that extra k data, and then that I call it CP. So, this particular one is called cyclic prefix, because it is a prefix. So, it is called CP, cyclic prefix, and then at the receiver what I do, this cyclic prefix I just remove it. How do I remove it? Just whatever data you observe it, do not take that first initial data. If the length is k here, don't take FastK data, that is it. Then what I should do? Obviously, my F is there. This is what I will get something. We will see what next. So, but what I am trying to say is that I have made my channel a simple circular channel. Okay. And then we will see what is the consequence of this case in the next classes. So, with this I end the session here for the basic WebDIM system, and we will see how the decoding has to be happening. Okay. So, in conclusion, we have kind of completed the and the reference will be same as what we have. Okay. Thank you.